All right. Let's have a look at the next concept. So if we can take one derivative, we can take more. And this is now introducing higher order partial derivatives. The partial derivatives, f sub x and f sub y, these are called there's a mistake here, these are called the first order partial derivatives. So those are the ones we've just introduced. We have been writing them with the df dx notation, but we can use subscript notation as shown here. So f sub x is the partial derivative of f with respect to x. So in other words, we're using, as a shorthand for this notation, we're going to use a subscript notation. And as a shorthand for the partial with respect to y, we're going to use this subscript notation. And so these are the first order partial derivatives, and we can start to compute derivatives of these functions now. And so in that case, we've got 4 kinds of second order partial derivatives. I can take the f sub x, or the partial of f with respect to x, and differentiate it with respect to x, or I could differentiate it with respect to y. I could also take the partial derivative of f with respect to y, differentiate it with respect to x, or take its partial with respect to y and then differentiate it with respect to y. Now to simplify notation, we're going to use this double subscript notation, fxx or fxy or fyx or fyy. But the important thing is to keep in mind which order the derivatives are taking place. And we can see here that with this second line, that the first derivative that gets taken is f sub x, and then that we differentiate with respect to y. So that means when we read this double subscript notation, we are going to read it from left to right. F sub x y means first differentiate with respect to x, and then differentiate with respect to y. Now we could use the d notation as well. And for the d notation, it means we first differentiate with respect to x, then we differentiate with respect to y. Since we place our differential operator, this d by dy, on the left-hand side of the expression, it means when we simplify the notation and remove brackets, and I write it in this simpler form, that I have to remember that I read it from right to left now in terms of the order of how the derivatives happen. The x derivative is first, and then the y derivative is second. So we read it from right to left. So we go right to left when we use the d notation, or if we use subscript notation, we go from left to right. So that's just an important thing to keep in mind. Depending on which notation you use, this will indicate which order the derivatives are to be taken. So let's have a look at this next example. Find the second and third order partial derivatives of the function given here. So we'll first find the x derivative. So that would be 3x squared minus 6xy plus 0, because the derivative of y squared with respect to x is 0. So there we've treated y as a constant and just looked at it as a function of x and differentiated it. Now we do the same thing for y. Treat x as a constant and differentiate with respect to y. We get negative 3x squared plus 2y. So there's our first order partials. Now we can go for our second order. We can go fxx. This means take the x derivative and differentiate it again with respect to x. So that would be 6x minus 6y. We could take the derivative of x with respect to x and then differentiate that with respect to y. So I'm using this one and then differentiating it with respect to y. And when we do that, we get negative 6x. Alternatively, we could take f sub y and differentiate it with respect to x. So that's this one, where we are differentiating with respect to x. And what do we get in this case? we get negative 6x. And then we get the derivative of y with respect to y is 2. So there's our 4 different second order partial derivatives. But in the question we were asked for the third order partial derivatives. So how many of those are we going to get? Well, let's think about that in advance. I can fill the 3 slots with the variables x, y, and z. So I can have 2 choices for the first slot, x or y, 2 for the second, 2 for the third. So there's really 8 different derivatives that we're going to have here. Let's see what they are. We got fxxx. So that's the derivative of fxx with respect to x. That's 6. Then we got the derivative of x with respect to y. So that's this one, where we're differentiating with respect to y. There we just did it with respect to x. When I differentiate with respect to y, I get negative 6. And now that takes care of fxx and the 2 possibilities for that third derivative, either x or y. Then we can go ahead and look at what about fxy, what about fyx, what about fyy, and all the possible derivatives there. But the thing to notice is that in the previous case with our second order derivatives, it didn't matter whether I did fxy or fyx because they ended up being the same thing. So we notice here that these actually were equal. And what we'll find is that in this case, we get the same result here, that as long as I'm doing one derivative is a y and 2 of them are x, the answer will always be negative 6. And we can just check that. So what is fxyx? fxyx means start with this one, fxy, and then differentiate with respect to x. And we see that we get negative 6 as a result. What about fyxx? fyx is this one. We're going to differentiate it with respect to x, and again we get negative 6. So even though there is 8 different possible derivatives, a lot of them just end up being equal. So we've dealt with all the cases where we've done 2 x derivatives and 1 y. Now let's look at 1 x derivative and 2 y's. So this is fxy, y. So we'll start with the fxy, and then we'll differentiate with respect to y. That's 0. Is that the same as fyxy and fyyx? We can check. fyxy, so there's yx, and then we differentiate with respect to y. That's 0. How about fyy with respect to x? fyy is 2, the derivative with respect to x is 0. So those are 3 more derivatives that are all the same, they're all equal to 0. So we've done no y derivatives, all 3 are x's. We've done 2 x's with 1 y, 1 x with 2 y's. The last case is all y's. fyyyy, and that's going to be this one here. The derivative of that with respect to y is 0. So we've got all 8 third order partial derivatives listed there. They actually came in one of 4 kinds. The one involving no y derivatives, the one involving 1 y derivative, one involving 2 y derivatives, and the one involving 3 y derivatives. Now it turns out, you may say, maybe this was just a coincidence. Maybe fxy was equal to fyx. So this part here, maybe that was just purely a coincidence that those were equal. It turned out that it wasn't a coincidence. We actually have a result. It's called the equality of mixed partials. And it is if the mixed partials fxy and fyx are continuous on a circular disk around the point in question, then the mixed partials are going to be the same. F of xy is going to be f of yx at that point. So that's a very nice result that we have, the equality of mixed partial derivatives. Now, we've just dealt with the derivative of a function of 2 variables. We can extend this. We can go for functions of any number of variables really, but here's the the next step, up to 3 variables. Really the difficult move, in some sense, is going from 1 variable to 2 variables. And we'll see that a lot in this course. We introduce, how do we go from a derivative of a function of 1 variable to 2 variables? That's this introduction of partial derivatives. But moving to 3 variables and 4 variables, we start to see the pattern. So going to higher dimensions is not as difficult as moving from essentially 1 or 2 dimensions up to the next dimension. And that's what's going to be our running theme of the course. We're going to introduce concepts by moving into the 3rd dimension, and then we'll see, oh, it's actually pretty straightforward to continue this pattern to move into higher dimensions. So how do we deal with the derivative of a function of 3 variables or even more? We just indicate which variable we are interested in. So in that case, that's our variable x. That is, how does our function values f change as x changes? Well, we just bump x up a little bit or down, so h can be positive or negative. We just move or change in the x direction a little bit and look at what happens with the difference in our function value at a given point f of x, y, z, and then a point a little bit away from that, f of x plus h, y, z. And then divide by h, look at what happens as the limit as h goes to 0. So the limit of this difference quotient, that is the x partial derivative. And in terms of calculating, it just means treat any variable that isn't x as a constant, and then just go ahead and compute the derivative with respect to x as you normally would in Calculus 1. So let's look at an example of this. Here's our function w of 3 variables, x, y, and z. We are interested in finding this derivative, the 3rd derivative of w with respect to z, y, and x. Now here order matters. We have to remember which derivative happens first, which one happens second, which one happens third. So the way we can think about this, again, you might want to think back, do we read this one right to left or left to right? But the other way to think about this is, how would we actually construct this? Well, the differential operator, the d by d, whatever the variable is, happens to the left of the expression. So we would start with w, then we differentiate with respect to x, then we differentiate with respect to y, and finally we would differentiate with respect to z. So that's how we unpack that notation. It's to be read from right to left. The rightmost expression in the denominator is the derivative that's happening first, and that's because when we write down using this d notation, the derivatives pile on the left-hand side of the expression. So let's go ahead and work this out. We need to find dw dx. What is dw dx? That is the derivative with respect to x of x over y plus 2z. Now we treat everything that isn't an x as a constant, so this derivative would just be 1 over y plus 2z, because the denominator is essentially a constant relative to x in this case. Now we're going to go ahead and compute the 2nd derivative of w, and that is going to be the derivative with respect to y of this expression we just calculated. So we want to compute the derivative with respect to y of 1 over y plus 2z. We could use the quotient rule here, or we could use a power rule by just noting that this is y plus 2z to the negative 1. In this case, I'll use the power rule, so the negative 1 comes down, and then our new exponent becomes a negative 2, so we get a y plus 2z all squared. And then the derivative of the inside, that's just a 1, because the inside is just y plus a constant. And so the derivative of y is 1. Now we're going to take that and differentiate it with respect to z. And so that means we want to compute the derivative with respect to z of negative y plus 2z to the negative 2. So again, I'll write it as a power. The derivative is the derivative of the outside function. That becomes a 2 times y plus 2z to the negative 3 times the derivative of the inside, which is 2. So that becomes a 4 over y plus 2z all cubed. And so there is our final result. Now lastly, maybe it's worth pointing out that if we wanted to use subscript notation instead of the d notation, as a subscript, or as subscripts, we would write this derivative as first differentiate with respect to x, and then with respect to y, and then with respect to z. So that's how we would write this using subscript notation, and the order would be read left to right in this case. Let's have a look at the last example. In this example, we want to verify this function of 3 variables is a solution to the 3-dimensional Laplace equation. So the second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z is equal to 0. So let's go ahead and see why this is the case. So we'll write out what u is, and I'm going to write it out as a power. So it's x squared plus y squared plus z squared to the negative 1/2. Because now when I differentiate u with respect to x, I can use the power rule. So that's negative 1/2 x squared plus y squared plus z squared to the negative 3/2 times the derivative of the inside, which is 2x. Because the inside function is x squared plus y squared plus z squared, and I'm treating the y squared plus z squared as a constant. So it's the derivative of x squared plus a constant, which is 2x. This becomes then negative x, and I will move it downstairs now as an x squared plus y squared plus z squared to the 3/2. Because now in the next step I'm going to use the quotient rule. We could have left it as a product and used the product rule, but I'm going to use the quotient rule here. So our quotient rule says it's the derivative of the top, which is negative 1, times the bottom, which is x squared plus y squared plus z squared to the 3/2, and then minus the top, so that's plus x, times the derivative of the bottom, which is 3/2 x squared plus y squared plus z squared to the 1/2, times the derivative of the inside, which is 2x. And then all of that is over the bottom squared. X squared plus y squared plus z squared all cubed. So there's our quotient rule. Now what do I notice? I can factor out a square root from both. So I'll factor out an x squared plus y squared plus z squared. In the first term, it's still there as an x squared plus y squared plus z squared, because I'm just looking at 3/2 as 1 plus a half. That's all I've done here, and I've got the power of 1 that I've just written down, and the half is the square root that I pulled out front. And then we've got our 3/2 2x times x, so that becomes a 3x squared, and then I've pulled out the x squared plus y squared plus z squared to the 1/2 all the way out front. So I'm just doing a little bit of simplification to the numerator. X squared plus y squared plus z squared cubed. And now with that numerator I can see I've got a negative x squared, negative y squared, negative z squared, and then I'm adding a 3x to that. So this becomes a 2x squared minus y squared minus z squared all over. That square root in the top can cancel with a little bit in the bottom to leave me with a power of 3 minus a half, or 2.5, or 5 over 2. So we've got a 5 over 2 as our power in our denominator, and that is our second partial with respect to x. Okay, so now we just need to do the second partial with respect to y, the second partial with respect to z. However, if we notice that our original function, there's a lot of symmetry in it. X, y, and z all appear in the same way. So if I was to compute the partial derivative, or the second partial with respect to y, we would just go through a similar calculation where everywhere I did something with the x above, I would be doing something with the y above. So it means that our resulting expression for the derivative would be negative x squared plus 2y squared minus z squared, all over that same denominator. So that's just by symmetry in the calculation. And we would also get the corresponding second partial with respect to z. It would be negative x squared minus y squared plus 2z squared, all over x squared plus y squared plus z squared to the 5/2. So now we've got all of the partial derivatives. So I will just say similarly, we got those next two calculations done. And so what are we interested in? We're interested in adding these things all up. And so therefore, we want to find the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. And if I notice what happens when I add them all up, they all have the same denominator, but what I end up doing is I add the 2x in the numerator to a negative x and a negative x. So those would all cancel. And then I have a negative y squared, a 2y squared, and another negative y squared. So those all cancel. And similarly for the z. And so we get that the sum is actually 0. And so we've just verified that. All right, so that's it for this section. What we've done is we introduced partial derivatives, the limit of a difference quotient, where the change is happening in the direction of the variable for which we're computing the partial derivative with respect to. We saw how to visualize this in terms of slicing our surface with planes and looking at the corresponding curves. And we saw how to calculate these things by just treating every other variable except the one we're differentiating with respect to as a constant, and just doing our regular calculus 1 derivatives for that particular variable in the expression. Next section, we will get into a little bit more geometry about where these partial derivatives can be used, for example, to find equations of tangent planes. And I already alluded to that a little bit in the first visualization that I gave you, where I constructed the tangent plane and we saw that it came about from finding the normal vector to the surface, which was the cross product of the two tangent vectors. We're going to carry that idea a little bit further in the next section. We're going to look at tangent planes and linear approximation. So thanks for watching, and we'll see you in the next section.